Welcome. This briefing will provide a technical overview of Himalayan slope instability, focusing on the causes of monsoon-induced landslides and the engineering strategies required to mitigate them. We'll begin by establishing the context of these monsoon disasters. Then, we'll examine the geophysical triggers and mechanisms, followed by the human factors that amplify the risk. From there, we'll cover engineering solutions and conclude with necessary adaptations in infrastructure and policy. The findings presented here are based on the comprehensive research conducted by Professor Ashutosh Kumar and his team, ensuring an evidence-based foundation for our discussion. Okay, first let's quantify the scale of the problem. Understanding the true cost of these monsoon events is critical. If we look at the 2023 monsoon season in India's Himachal Pradesh state, the data is stark. There were 428 confirmed fatalities directly attributed to landslides and extreme rainfall. The economic impact was equally severe. Damage to infrastructure, including thousands of structures and critical transportation links, resulted in estimated losses of $1.2 billion for that region alone. By 2025, the transboundary nature of this issue became impossible to ignore. Fatalities in India surpassed 1,500, while Pakistan recorded over 1,000 deaths from related floods and landslides. It's clear this is a regional crisis, not a localized one. Now let's move into the core geomechanics. What are the specific natural triggers and geological conditions that predispose these slopes to failure? This map is quite revealing. You'll notice the cloudburst events. These periods of extreme, high-intensity rainfall are not randomly distributed. They are heavily concentrated in the Lesser Himalayan sequence, which is a zone characterized by both tectonic activity and weak lithology. So, how does the rain actually induce a failure? It's a well-understood three-step mechanism. First, rainfall infiltration saturates the slope. This leads to an increase in pore water pressure as water fills the voids between particles. This pressure effectively pushes the particles apart, which reduces the effective stress. That's the internal friction holding the mass together. When that stress drops below a critical threshold, failure occurs. The underlying geology or lithology is a key precondition. Much of this region, particularly Himachal Pradesh, is composed of weak rock like sandstone. These formations have very low strength, especially when they become saturated, making them highly susceptible to weathering and collapse. While natural factors set the stage, it's really the human activities, the anthropogenic factors, that act as a multiplier, turning these hazards into widespread disasters. Research points to 4 primary factors here. Unscientific slope cutting for road construction destabilizes the natural angle of repose. Unregulated construction adds significant load to already fragile slopes. And of course, deforestation removes the root systems that bind soil, which in turn disrupts natural surface and subsurface drainage patterns. And as researchers Sana and Kumar noted in their 2026 paper, it is precisely this cumulative effect of human activity that elevates a natural phenomenon into a large-scale disaster. So, given this understanding, let's turn to the solutions. What are the practical engineering-based interventions that can build slope resilience? From a geotechnical perspective, there are several urgent solutions. We have active stabilization techniques like soil nailing and anchoring. We can implement comprehensive drainage systems to manage that critical pore water pressure. We can also use reinforcement materials like geosynthetics and retaining walls. And crucially, deploy real-time monitoring to provide early warnings. This requires a fundamental shift in how we approach highway engineering in the region. Standard drainage design is no longer sufficient. It has to be designed for much higher rainfall intensity. Basic slope cutting has to be replaced with engineered slope protection. And route selection can no longer just be about the shortest distance. It must be planned based on a deep understanding of geological fragility. Of course, these site-specific engineering fixes must be supported by a larger framework of adaptive infrastructure planning and regional policy. The policy recommendations are clear. First, mandatory hazard zonation is needed for risk-informed land use. Second, we need strict enforcement of building codes in these zones. Third, geotechnical risk assessments must be integrated into all development projects from the outset. And finally, because this is a transboundary issue, we need protocols for sharing hydrometeorological and geological data across borders. And that brings us to the final, forward-looking question. Acknowledging that these geohazards cross international borders, What specific frameworks are required to evolve from simple data sharing to a truly integrated, international approach to risk mitigation for the entire region?